All right, in this video, we're going to go through implicit differentiation, which sounds like a very complicated term, but it's actually not. And it has to do with regular differentiation, or taking your derivatives. So as of right now, we should feel pretty comfortable finding the derivatives of your typical everyday functions, such as x squared, 3, and then this one will simplify a little bit to find the derivative. Now, normally, when taking derivatives, we kind of skip over this part because it seems redundant, but if I take the derivative of y equals x squared, what you're essentially getting is the derivative of your function y, and we do it with respect to x. And now that might sound a little bit funny, but technically, when we're finding our derivative, we're finding an instantaneous rate of change, right? And if you were going to find a rate of change, so like speed, you would want to be specific with what you were finding speed in respect to. So would you be doing miles per hour? Or would you be doing miles per minute? Or miles per second, right? So am I taking or are you comparing like miles per meter or something like that, right? That one's not as common, obviously, for speed, but you have to be, if I'm taking the derivative, I'm finding the rate of change of miles over time, you want to be specific with what you're taking the rate of change with respect to. So technically, when we do our derivative, and that's why one of our notation is dy dx, then you take the derivative with your variable with respect to x. Now, when we do this on the right-hand side, we get 2x, and then technically you're taking the derivative of x with respect to x, but this, as we can see, is not very pretty in math, and it doesn't really make sense as far as leaving it on every single time, because obviously if you're taking the derivative of x with respect to x, you don't need this notation piece that's on here. So we usually don't write that part of it. We usually just write this part of it, and then there are other ways we can write a derivative as well. Derivative of y equals 3, so the derivative of y with respect to x would just be 0, and then you would write dx dx, right? There's no x over here, but you're still taking the derivative with respect to x. On this side, we'd work with it a little bit first probably, so we get y equals 4x to the 6th plus 12x to the 5th. So then we can find the derivative of y with respect to x, and we'd get 24x to the 5th. Technically, you'd want to write dx dx, but we don't do that because it's a waste of time. And then 60x to the 4th, dx dx, but again, you see how that part would get very redundant. Okay, so we know how to take derivatives of these functions. Now, not all equations are as pretty and as simple to differentiate. So for example, this is an equation that makes a conic section, right? This is an ellipse, x squared plus xy plus y squared. And although it's not our typical function, we can still find the slope of a tangent line at any of these points. So like if I picked this point right here, I could still find the slope of the tangent line, which means I still have to be able to find the derivative. Or I could pick a point over here and do the same thing. And so we are going to learn a method for differentiating this called implicit differentiation. And so these are your steps for implicit differentiation. So you want to differentiate both sides of your equation with respect to x. You notice how this isn't solved very nice and neat for y. That's what makes it a problem that you'd have to use implicit differentiation for. And then whenever you differentiate or find the derivative of a variable y, you need to, and I put this in quotes because it's not mathematical, but tack on a dy dx. And then at the very end, we want to solve for that dy dx. Okay? Just the same way that I was showing you, we take the derivative of y with respect to x up here. We need to still do that, even if y isn't what your equation solved for. So we're going to try that. So let's go ahead and look at our first example. So if x squared plus y squared equals 25, it's a nice circle equation. This isn't solved really easily for y, so I'm going to use implicit differentiation to differentiate, or to find the derivative. So the derivative of x squared is still just regular, so it's 2x. The derivative of y squared is just 2y, but because I took the derivative of y, I need to, quote, tack on a dy dx. And then what's the derivative of 25? Well, the derivative of 25 is 0. And so then now I'm going to solve for my dy dx, my derivative, and that will give me my answer. So I'll subtract the 2x over, and I get 2y dy dx equals negative 2x. Then I have to divide both sides by 2y. So at the very end of all this, I get that my derivative at any point on the circle, so my slope of your tangent line, whether I draw a point here, whether I draw a point here, etc., my derivative will be the function, let's see, negative 2x over 2y, choose cancel, so negative x over y, excuse me, not function, but equation. So this would be my derivative. Okay. All right, let's try another example. So in this one, got this nice little loop-de-loop here. So the equation that makes this graph is x cubed plus y cubed equals 6xy. So I'm going to do the same thing, find dy dx first, and then I'll have to find the slope of the tangent line at a particular point. So let me go ahead and just find dy dx first. Oh, geez. Stop doing normal derivatives. Derivative of x cubed is 3x squared, and I don't need to write dx here, plus 3y squared, and then I took the derivative of a y variable, so I need to tack on a dy dx. Okay, and then on this side, I know it's a little tricky to see, but technically you have the product rule because I have a 6x times a y. So I'm going to just off to the side find that derivative on its own. So my f function is 6x, f prime would be 6. My g function is y, and so the derivative of y is 1, but because I took the derivative of y, I get dy dx. That's g prime. So then I do crisscross applesauce, and I'll end up with 6x dy dx plus 6y. Okay, and then this one looks a little bit harder to solve, but as a kind of note to yourself, if you run into a complicated equation, looks like it's complicated to solve, there are a couple of little reminders. I would say get all your dy dx on one side of the equation and everything else on the other side. So now I'm going to go ahead and I'm going to do that. I'm going to get everything that has a dy dx on one side of my equation and everything that doesn't have a dy dx on the other side. So let's see. I'll subtract over the 6x dy dx over here. And then that means so that all my dy dx's will be on the left side of the equation, and then I'll move this 3x squared over here. Okay, so that's gone on that side, that's gone on that side. So I'm left on the left-hand side, I have 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. And then now, because on my left-hand side I have two terms, right? I have something minus something else, so I have two terms. I can pull out the dy dx as a GCF, essentially. So I'll have dy dx times 3y squared minus 6x equals 6y minus 3x squared. And then now to get dy dx by itself, I just divide both sides by 3y squared minus 6x. So I'm running out of room, but my final answer would be dy dx equals 6y minus 3x squared over 3y squared minus 6x. And the only thing that you can simplify in here is if there is maybe a number that all of your constants are divisible by. So these are all divisible by 3. So I can go ahead and reduce them all. So that would just be a y squared, that would just be a negative x squared. And this would be a 2 and a 2. But I can't cancel x's because I got subtraction going on. I can't cancel y's because I have subtraction going on. Don't go crazy, all right? And then this is your final answer. When you are working through problems, depending on which side you decided to move your dy dx's over to, your answer could either end up like this, or it could end up with the complete opposite symbol. So I could end up with negative 2y plus x squared over negative y squared plus 2x. This would also be a perfectly correct answer. So if you're working on practice problems and you're checking them against the answer key, for example, your answer might look very exactly the same, but it might have completely opposite signs from mine, and that is fine. That means it's also correct. Okay. All right, so that's your dy dx. And then to find the slope of the tangent line at 3, 3, all we have to do now is we have to plug 3, x equals 3 and y equals 3 into dy dx. So I'm essentially, here's the point 3, 3, I'm essentially finding the slope, of that tangent line by plugging the point into my derivative function. And usually the notation for this is if this is my general derivative, so if I wanted to plug in a specific point, you'll see this a lot. So dy dx calculated at 3, 3 would equal 2 times 3 minus 3 squared all over 3 squared minus 2 times 3. So I would get 6 minus 9 on top, so I'd get negative 3. I get 9 minus 6 on the bottom, so positive 3. So my slope of my tangent line here is negative 1, and that kind of makes sense. It kind of looks like it goes through 6 and 6 here. So there you go. So that's another implicit differentiation problem. Let's try another example. All right, so this equation makes this graph super fun. And so now we're going to find the derivative of this using implicit differentiation. And I think this will be the last example for this part of the video. So first thing I'm going to do is start off with my left-hand side. Derivative of 3y squared would be 6y. And because I took the derivative of y, I tack on a dy dx. And then on the right-hand side, right here, I notice that I have a product going on. I have an x squared times a y cubed. So if I have x squared, that means f prime would be 2x. And then if y cubed is my g, then 3y squared dy dx would be my g prime. Crisscross applesauce. And I would get, let's see, 3x squared y dy dx. I know the 3 goes with the y squared, but I hate not writing the constant in the very front. So they're all multiplied. Oh, I gotta be careful, that's a y squared. And then plus 2x times 3, or y cubed, so 2x y cubed. And then I don't forget about you have a plus 4x just tacked on to the end, so find the derivative of that and you get just plus 4. All right, and so then now I'm going to do the same thing in the previous, as I did in the previous example, where I get all my dy dx's to one side. So it looks like the only thing I have to move over is this guy. Oops. Cancel from that side. So I have 6y minus, dy dx minus 3x squared y squared dy dx equal 2x cubed plus 4. Pull out my dy dx as a greatest common factor. And I get 6y minus 3x squared y squared. And then to get my dy dx by itself, I just have to divide both sides by the stuff in my parentheses. So I get dy dx is 2xy cubed plus 4 over 6y minus 3x squared y squared. And in this scenario, there is no number that goes into 2, 3, 4, and 6, and I can't cancel anything else in any of my terms because there's nothing that's the same in every single term. So that would be my final answer for this problem. All right. That's the end of this video, so either take a break and move on to part 2, or just keep pushing through.